Chapter 5 deals with the application of Newton's laws of motion that we saw in the previous chapter. Because we'll be doing a lot of applications, a lot of problems, I thought the most useful video would be one which showed you 2 sample problems. So today we're going to focus on equilibrium. In equilibrium, the equation that we use is that the sum of the forces is equal to 0. This means the acceleration is 0. There's 2 types of equilibrium. Static equilibrium means there's no motion. And dynamic motion means the motion is with a constant velocity. Of course, you can see that in both these cases, the acceleration is 0. When we use the sum of the forces equal to 0, keep in mind that this is going to break down into component form. Well, first we can look at forces in the x direction, and they add up to be 0. And then we look at the forces in the y direction, and those add up to be 0 as well. So this is where it's going to be important for us to remember how to write the components of forces. And when we're looking at these individual equations, where we're looking at x and y, we have to use a consistent sign convention. For instance, to the right is positive, to the left is negative. For the y direction, up is positive, down is negative. I mean, you can actually use whatever sign convention you want, as long as you're consistent. Okay, so this is our first problem. This is a really common type of problem, which is why I chose it. We have a series of cables that are connected and then are suspending and holding up a weight. And the other reason I like this problem is because you're not given numbers, which always makes everyone uncomfortable, but you have to get used to it. Now, in this type of problem, I find it useful to sort of do it in 2 parts where we're going to focus on 2 areas. The first part, we're going to focus on the fact that cable C is supporting the light. So that's going to be a free body diagram that we work with. And then next, we'll focus on this point where the 3 cables intersect and look at the forces acting at that point. All right, so first, like I said, we're going to focus on the cable and the weight that it supports. If we draw a free body diagram, so I'm just going to make this is the light and this is the cable. There's a force acting up on the cable due to the cable, and I'm going to call that T sub C, the tension in cable C. And there's a force acting down on at the light. It's the weight of the lantern, which we're just going to call W. Sometimes that might be mg, but in this case, since they gave you the value of W, we're going to stick with that. If you look at this, this is our free body diagram. It's not fancy. You don't have to be fancy. But if you want to, you can do that too. Now we want to apply our laws of equilibrium. Now in this problem, I notice that the only forces I have are in the y direction, so I don't have to worry about using the x coordinate or the x forces. And I'm going to say up is positive and down is negative. So T sub C is positive minus W equals 0. So I find right away that the tension in cable C is equal to the weight of the lantern. You may have really sort of assumed that that was true, but it's always nice to do the work and to show that that's how it works out. Next, I'm going to focus on this point where the 3 cables intersect and look at the forces acting at that point. Again, that point is in equilibrium, so we can apply the rules of equilibrium as well. So I'm just going to redraw it here, and there, and down, and using the fact that alternate interior angles are equal, I know that this angle is 45 degrees and this angle is 30. And so now I'm going to draw my forces. I have the tension in C is going to pull down. And that's true because remember, ropes or cables can never push, they always pull. Then I have tension sub B here and tension A here. Keep in mind I'm going to have to break down each of these tensions into their x and y components. And so I'm going to have to remember how to write them when I use my conditions for equilibrium. My conditions for equilibrium for this drawing, of course, I have to look at forces in the y direction and forces in the x direction adding to 0. So I'm going to have two equations there. I'm going to go to the next page so I have a little bit more room. And I'm going to just draw my forces on here just to remind us of what we were looking at in the previous slide. Remember that this is 45 degrees and this is 30 degrees. So forces in the x direction are 0. Notice that cable B and cable A have x components, and they're both going to be given by, they're the side adjacent to the angle, so they'll be given by the cosine. So if TBX is in the positive direction, it's to the right. TAX is negative because it's pointing to the left. The x component of cable B is given by T sub B times the cosine of 45 degrees. The x component of cable A is T sub A times the cosine of 30 degrees. And those add up to be 0. And so this is our first equation that we have that we're going to be working with. In the y direction, we have y components of A and B, and then of course TC is straight down. The y components of A and B are both positive, and TC is of course negative. The y components, because they're given by the side opposite the angle, are given by the sine. And I'm also going to make the substitution that T sub C is equal to the weight, W. And this is the second equation that I have. Now, these are two equations. Now, this is just an algebra problem. I have two equations, two unknowns, T sub A, T sub B. I'm going to take equation 1, and I'm going to solve for T sub A in terms of T sub B. And then what I can do is I can take this and substitute into the second equation to, now that would make an equation that only has T sub B as an unknown. So that's T sub A, and then times the sine of 30, plus T sub B, sine of 45, minus W, equals 0. I notice that this is equal to the tangent of 30 because the sine over the cosine. So if T sub B times the cosine of 45 times the tangent of 30 plus T sub B sine 45, and I'm going to put W on the other side. I can also factor out T sub B, and I'll get cosine of 45 tangent of 30 plus sine of 45. And then I keep in mind this is just going to be a number, and it turns out that that number is 1.115. So I have T sub B times 1.115 is equal to W. So T sub B is equal to W over that number. And that can be written as 0.897 W. Now, T sub A, remember, is T sub B times the cosine of 45 over the cosine of 30. So I can take this value and substitute it in here to find T sub A. T sub A turns out to be 0.732 W. And so I have found T sub Z is W, T sub B is 0.897 W, and T sub A is equal to 0.732 W. And that is what I was asked to do. So hopefully you can follow that, but these things take practice, but you'll notice that you'll see patterns and get used to the process. The next problem I wanted to look at was an inclined plane problem. And the reason I wanted to focus on an inclined plane problem is we want to remember that for inclined planes, we made the choice to alter the way we draw our XY coordinate system. We draw the x-axis so it's parallel to the surface of the incline, and then the y-axis is perpendicular to the surface. What happens then is we have the weight mg acts downward, straight downward, so it's at an angle. It's not strictly in the y direction. This angle right here between the negative y-axis and the weight ends up to be the same as the angle of the incline, and you can show that that's true. It's just simple right triangles relationships. And so you're going to have a y component of the weight and an x component of the weight. The y component is going to tend to be pushing the object into the surface of the incline, while the x component is going to tend to be taking the object down the incline. Notice, because of the way the angle's defined, that mgy turns out to be mg times the cosine of 25 here, while mgx is mg sine of 25. So it's a good example of why you don't want to assume that a particular direction has a particular sine or cosine with it. All right, so that's just reviewing the inclined plane. Let's take a look and draw the picture of all the forces acting on this car. I have mg acting straight down. I have the tension in this cable, and then of course I would also have the normal force that would act straight up. The car's not moving, so the sum of the forces in the x direction is 0. The sum of the forces in the y direction is 0. I'm going to start with the y direction just for extra practice. It turns out, well, we'll see how we use that. We have normal minus mgy plus t times the sine of 31 degrees is equal to 0. So the normal is purely in the y direction, and it's positive. The tension in the cable has a y component given by t times the sine of 31. That's the angle it is above the horizontal. And then mgy, well, let's just write what that is. Remember that mgy would be mg times the cosine of 25 degrees. Okay, and so remember that what we're trying to find is the tension in the cable. This equation right here really can't help us find the tension in the cable unless we know what the normal force is. So let's take a look at the forces in the x direction. In the x direction, I have the x component of the tension and then the x component of the weight. The x component of the tension, is t times the cosine of 31 degrees, and the x component of the weight is mg times the sine of 25 degrees, and that's equal to 0. It turns out that the mass we're given is 1,000 kilograms G is 9.8. Notice I just put 9.8. I don't put a negative sign. I've already determined that the weight acts down because of the fact that G is negative, so I don't need to do that. Now this is an expression, this equation that we come up with for the x direction is the one that we're going to be able to use to find the tension. We just rearrange. So a lot of this ends up being algebra after you identify your forces and write your components. And it turns out here then our tension is 4832 newtons. So hopefully you find these two examples helpful. They're certainly not an exhaustive idea of what kind of problems you'll have, but they are two really nice examples of objects in equilibrium.